All right, so we've had a bit of a setback. I'm not going to deny it, and I'd be lying if I said I wasn't disappointed. But while we were proving all those important theorems last time, the fire spread, and now instead of just one sync vertex, we have three of them. And the reason why this puts us in a bit of a tough spot is that the important results that we proved last time, results like how do we know when a flow is truly maximum, and how can we compute a maximum flow in polynomial time, well, those results were only proven for the case where the flow network had one source vertex and one sink vertex. So for example, one thing we saw last time, by means of a very complicated and exhausting proof, was that the Edmonds-Karp algorithm does indeed compute a maximum flow, and it does so in polynomial time. But again, that only applies to flow networks with one source vertex and one sink vertex. And while I guess I can brainstorm various ways to adapt the Edmonds-Karp algorithm to handle multiple sink vertices, it's not clear to me that the proofs that we wrote will generalize to that case. So in other words, we might have to start again and prove that the Edmonds-Karp algorithm or some other algorithm actually computes a maximum flow and that it does so quickly if we want to handle the multiple sink case. Okay, fair enough. That's a setback. Now, as always, we can't panic in a situation like this. Even though it is getting a little bit out of hand, we have to take a step back and be scientific and find some way of calmly and methodically coming to a solution to this problem. No pressure or anything. All right. Boy, it's getting hot in here. I could really go for a popsicle right about now. Actually, speaking of which, I've been trying to be a little bit more intentional with my sugar consumption. I don't know, maybe it's the pressure of making all these lecture slides or whatever, but I find that this summer I've been eating a bit too many sugary dessert things. And so I don't want to deprive myself completely. I don't really think that's the way to go about this. I just want to be a little bit more careful not to eat any more sugar, I guess, than I have to get as much enjoyment as I can out of a bit less, I don't know, sugary frozen desserts. So what I know is that I like to have all of these different types of frozen novelties in the summertime, and they all come in a variety of delicious fruit flavors. Now, there are 6 different types of frozen refreshment that I want, and it actually turns out that across this entire list, there actually are 6 distinct flavors. And I guess what I want to do maybe is just pare down the number of items that I consume while still getting to enjoy the full variety of different types and different flavors. So I guess my question is it possible to choose 6 different items from this table without repeating any types or flavors? In other words, is there a way for me to sample one of each type and one of each flavor without repeating anything and still get one of each of the different types and one of each of the 6 flavors? I've thought about this problem a lot. And what I realized is that I could model the problem using a bipartite graph. Basically, what I could do is make a vertex over on the left for each different type of frozen refreshment and a vertex over on the right for each possible flavor. Now, I'm using this word bipartite graph. I guess I should remind you what that means. We saw that way back in, I think, lecture 27, so a while ago. But a bipartite graph is an undirected graph where the vertices can be partitioned into 2 sets x and y, such that all of the edges of the graph pass between x and y. So they have exactly one endpoint in x and one endpoint in y. It is not a bipartition if you have any edge between 2 vertices in x or any edge between 2 vertices in y. We also saw that it's possible to compute a bipartition of a bipartite graph. So if the graph has any bipartition, it's called a bipartite graph. It's possible to compute such a thing, so the partition xy, in linear time using a basic graph traversal algorithm adapted, I think in lecture 27 we described it in terms of coloring vertices red and blue. So basically what I could do is model the possible frozen refreshments using a bipartite graph where I use a vertex to represent each type and a vertex to represent each flavor, and the items themselves then become edges connecting a particular type and flavor. So for example, this edge here indicates that there is such a thing as banana frozen yogurt, and this edge down here indicates that there is such a thing as a raspberry snow cone. On the other hand, the fact that there is no edge from freezy to banana implies that there is no such thing as a banana freezy. So my original question was, is there a way for me to choose a collection of 6 items without repeating types or flavors? So I get every single flavor once and every single type once. Well, a selection of items of any size can correspond then to a subset of the edges of my graph. So the edges I've highlighted here, the blue edges in this example correspond to, well, I've got a grape popsicle here, I have an orange snow cone down here, and finally I have raspberry frozen yogurt here. So I found a collection of of 3 different things where I do not repeat types or flavors, I guess what I want is to see whether I can find a collection of 6. Now notice that with this particular collection of 3 things, it actually isn't possible to expand it. So once I've chosen my grape popsicle, orange snow cone, and raspberry frozen yogurt, I cannot add any more items to the mix without repeating a type or a flavor. So for example, if I want to add a freezy to this collection, my choice is either a grape freezy, that would be this edge here, which I can't choose because I've already used the flavor grape for something else, or I could choose a raspberry freezy, but then that would also be a problem because I've already chosen the flavor raspberry for something else. So what this is sort of telling me is either that I can't make a collection with more than 3 items in it, or maybe that making such a collection, making a collection of size 4 or 5 or 6, is a little bit more challenging than, I guess, my first attempt might have just been to keep picking up edges of the graph as long as they don't share an endpoint. But I found this collection of size 3 that can't be expanded. And certainly I hope, for the sake of my summer refreshment, that it is possible to pick up, I don't know, at least 4 different items that don't repeat types or flavors. So it actually turns out that I can create a collection of edges that corresponds to a selection of 4 items. So in this case, I still have an orange snow cone and a grape popsicle, but I've switched flavors of frozen yogurt, so I now have banana frozen yogurt, and that frees up the raspberry flavor for me to have a raspberry freezy. So I guess what that's telling me is that just because I can make a collection of a certain size doesn't necessarily mean I can expand that collection to be a collection of maximum size. So I suppose my question then becomes, how can I construct a maximum size selection of refreshments with no repeated flavors or types? And to do this, we could study something called a matching in a bipartite graph. So a matching in any graph, it turns out matchings are defined for all types of graphs, all undirected graphs, not just bipartite ones. A matching is some collection M, which is a subset of the edges of the graph, such that the edges in the collection M are disjoint. So these edges do not have common endpoints. And we can observe that the blue edges I've shown here correspond to a matching. They are a matching of size 2, because notice that this edge and this edge here do not share any common endpoints. Each vertex is covered by at most one of the edges in my collection. As I said a minute ago, matchings can be defined for any type of graph, not just bipartite ones, although for the sake of this application, I'm going to focus only on bipartite ones. I'm going to come back a bit later to the subject of matchings in general, just to sort of tie up that loose end, but the only results we're really going to see today are related to bipartite matchings. All right, just some comprehension stuff before we get started. Is this a matching? Are the 4 blue edges shown here, do they constitute a matching of this graph? And it turns out that the answer is no, because if I look at that vertex there, notice that there are 2 edges in my collection that share an endpoint. And so that means this collection of 4 edges is not a matching. I should also observe that the empty set is always a matching. So if I choose 0 edges, there's no way they're going to share any endpoints, so the set of nothing is a valid matching. Additionally, if I choose any single edge, so here's a single edge here, notice that if I put this edge in a collection by itself, certainly the resulting collection will be a matching, because there's no way that an edge shares an endpoint with itself, under the definition we have been using all along of all graphs being so-called simple graphs, where it's not valid for a graph to have an edge that connects a vertex to itself. Such things might exist, but in this course, if we say graph, we always mean simple graph, and so these loops are not allowed to exist. So I think what this is telling me is that constructing small matchings is easy. I can make a matching of size 0 trivially by having nothing in the collection. I can make a matching of size 1 also basically trivially. As long as my graph has edges, I can create matchings of size 1. On the other hand, things get a bit more complicated the more crowded the matching gets. The more things I want to put in my matching, the more challenging it is to construct a matching of that size. So I suppose what that's telling me is that the matchings I'm looking for, large matchings, are hard to find. And that if I want to look at the most interesting or challenging matchings, what I'm looking for are maximum matchings. So a maximum matching is a matching M of maximum size across all matchings for a particular graph. So we have an optimization problem already. Well, that's nice. We've just spent a long time in this course talking about optimization problems. Okay, so how about this? Here is that matching of size 2 from earlier. Is this a maximum matching? And before I address the question, I want to observe that, well, either the answer is yes or no, certainly. Either it is maximum or it isn't. If it isn't maximum, one easy way for me to prove that is to show you a matching of size 3. Because certainly if there's a matching of size 3 out there, this is not a maximum matching. Okay, that's the easy case, I guess. If this matching is maximum, how do I prove it to you? Just because I can't find a matching that's larger, does that necessarily mean that such a matching doesn't exist? That's a bit of a tough question. It reminds me quite a bit of a question we had to deal with over the past couple of lectures, which is I find a flow that I think is maximum, but it's really hard to show that it's maximum without some extra theoretical machinery. So one way we can show a flow is maximum is the Max-Flow Min-Cut Theorem. If we find a cut with the same capacity as the value of our flow, we know that the flow is maximum and the cut is minimum. So I want to observe that with any maximization or minimization problem, we could run into this issue where we have a solution that we strongly believe to be the optimal solution, but it's very hard to show it. It's very easy to disprove that a particular solution is optimal by just finding a better solution. But what if we already have the best one? How do we show that? So it turns out in this case that this matching is not maximum. And one easy way for me to prove that is to show you a matching of size 3. Okay, so here's a matching of size 3. Because we can verify very easily that this is a matching, that very clearly disproves that this is a maximum matching. Now, notice if we go back to our matching of size 2, notice that although it is not maximum, I can't make it any bigger. So if I leave these two blue edges in my collection, observe that all of the edges remaining, that would be this one, this one, this one, this one, this one, and this one, all of those edges have to be excluded from the matching. I can't add any of them because they would conflict with edges that are already present. So for example, if I add this edge here, I'd have a problem with two edges sharing an endpoint, which means that the matching that I've come up with, this matching of size 2, although it's not maximum, I can't make it any larger. I guess we could call such a thing maximal. That's the term typically used for local optimal solutions. So this particular matching can't get any bigger. It's maximal, but it's not maximum because there is somewhere out there a matching that is larger. What this is sort of hinting at, and we saw the same case earlier with the frozen refreshments, what this is sort of hinting at is that finding matchings isn't as easy as a simple greedy algorithm would imply. So I guess one obvious algorithm that I might try first if I want to generate a large matching is an algorithm that just goes through the graph and keeps picking up edges as long as there are edges that exist that don't share endpoints with any of the edges I've already chosen. That's what I consider to be a very straightforward greedy algorithm. And this example here, the fact that there exist matchings out there that are maximal but not maximum, pretty much demonstrates that that simple greedy algorithm isn't going to work in general. Maybe I'm lucky, but in general I can't expect that I will be. Okay, so finding maximum matchings apparently is non-trivial. It does require a bit of thought, or I might have to back up and try again. Now earlier in the course, for example, when we were talking about dynamic programming, when we talked about the longest common subsequence problem, for example, we observed that obviously the natural thing to do when you encounter a new problem is to try very simple algorithmic approaches and then try and prove them wrong. So verify that they're actually just a heuristic that might work in some cases versus an algorithm that works in all cases. What I've shown here is that a basic greedy algorithm doesn't work, and so I suppose that means I ought to treat this problem with respect. It might be a harder problem than it seems on the surface. So I guess that's our task. Let's design an algorithm to compute a maximum matching of an undirected bipartite graph G. So one observation I can make right off the bat, and this, I guess there's a benefit that I have from the fact that the graph is bipartite. I know that I can divide the graph up into this bipartition x, y, and in this lecture I'll always put x on the left and y on the right, although fundamentally they're interchangeable. I know that every edge has to go between x and y. And so what's sort of nice about that is it's really easy to characterize the way these edges have to look inside the matching. So this is the thing I'm about to say. The observation on this particular slide actually holds even for graphs that aren't bipartite. But since every vertex can be incident to at most one edge in a matching, if I want to maximize the size of the matching, I'm also maximizing the number of vertices incident to edges in the matching. So if I think of a particular matching, let's just make one up on the spot here. So here is a matching here. Notice that it has two edges, and because those two edges can't share endpoints, the number of vertices involved in the matching is equal to 4, so double the number of edges. So maximizing the number of edges in the matching is basically equivalent to maximizing the number of vertices entangled in those edges. So for example here, I have a matching of size 3, and it includes 6 vertices. And I can just count off those vertices with this +1 notation that's sort of ringing a bell from something that I've seen recently. That's sort of interesting. And I'll go back to the fact that visualizing a bipartite matching does sort of lead us to, I guess, if we think of it in sort of a left to right order, what I could think of happening here is that what I'm doing is pairing up vertices in X with vertices in Y. I'm using this +1 notation, but given what we've seen over the past 2 lectures, I'm sort of tempted to begin adding directions to the mix as well. I could sort of view this matching as a way of transporting something from left to right. I'm moving, maybe flow across from vertices in X to vertices in Y. So I could even add a direction to these edges and sort of begin visualizing what's really happening here as one unit is being pushed from a vertex on the left, a vertex in X, into a vertex on the right, into a vertex in Y. So if xy is a bipartition of the graph, all of the edges obviously must cross between x and y. So for any matching m, exactly size of m vertices in x must be involved in my matching, and exactly size of m vertices in y must be involved in my matching. And they must be endpoints of edges in the matching. So here's an idea. As I mentioned a minute ago, let's just add edge directions so that every edge points to the right. Every edge points from x to y. And then this begins to look a bit like a flow problem. The reason why I think a flow problem is a useful adaptation here, it's a useful model to use, is that the restriction I'm trying to enforce, which is that no two edges in my matching share an endpoint, seems to be something that I might be able to enforce using capacity constraints, but not in the most obvious way. So if I add directions to my edges, I'm one step closer to having a flow network. But of course, to have a flow network, I need source vertices, maybe at least one of them, sink vertices, or at least one sink vertex, and edge capacities. And I will observe that there is a certain capacity-related flavor to this problem. I want to make sure that every vertex participates in the matching at most once. It is not attached to any more than one edge in the matching. But setting a capacity on the edges isn't necessarily going to achieve that for me, as I'm going to show over the next few slides. So if I want to treat this as a flow problem, I need, basically what I'm trying to do is route flow from vertices in X to vertices in Y, such that at most one unit of flow leaves each vertex in X, and at most one unit of flow enters each vertex in Y. It feels like if I can enforce those capacity constraints, I will indeed actually have a matching when I'm done. The edges that I use to transport units of flow will then be edges in a matching. So to do this, of course, I need source vertex, sink vertex, and edge capacities. So it's sort of tempting to say, since I'm pushing flow from X into Y, let's just call every vertex in X a source vertex. Now the problem with this is that we already know one of the characteristics of a source vertex is that a source vertex has access to an unlimited supply of flow. We're not allowed to limit the amount of flow leaving the source vertex except with the limits on the capacities of individual edges. But that's not quite going to do the trick here, because if I set the capacity of this edge to be 1 and I set the capacity of this other edge to be 1, well then I suppose there could exist a flow where I use both of those edges. I push one unit through both of them. There's no way to restrict that only one unit is ever allowed to leave this vertex here if we call this vertex a source vertex, if we allow this vertex to have all the privileges of a typical source vertex. So what I want to do is add enough other vertices to constrain the amount of flow passing through a particular vertex. One observation I can make right off the bat here is that if this were an intermediate vertex, it would be fairly easy to constrain the amount of flow passing through it. Because although I can't necessarily constrain the amount of flow that leaves it directly, because there could be multiple edges leaving it, I could arrange that there is only one incoming edge, and that incoming edge has a capacity of 1. And if I do that, I can pretty much guarantee that no more than one unit of flow can ever pass through this vertex. So certainly that wouldn't work if this vertex is a source vertex. Now, the other problem, obviously, is that we have no idea how to deal with flow networks that have more than one source vertex. Although, I guess we're going to have to figure that out eventually. And similarly, if I were to make every vertex in Y a sink vertex, we do not yet know how to handle networks that have more than one sink vertex. Okay, so I've just indicated that not only do we not know how to handle the case where there are multiple source vertices, it wouldn't really help us here anyway. What I'm going to do instead is add another source vertex over on the left and connect it to every vertex in X. I'm going to make every vertex in X an intermediate vertex. As I said a minute ago, that is going to allow us to restrict the total amount of flow entering those vertices in X, and therefore by extension leaving them. Okay, so I add a brand new synthetic source vertex S, and I connect it to every vertex in X via an edge of capacity 1. And then symmetrically, I need a sink vertex, and And this trick here of having a source vertex connected only to vertices in X allows me to govern the total amount of flow passing through them, because flow conservation requires the amount of flow leaving a vertex in X to match the amount that enters it. I want to do something symmetric for vertices in Y. So what I'll do is define a new sync vertex over on the right, and I will attach every vertex in Y to my new sync vertex, again with an edge of capacity 1. Now, what I'm setting up here isn't a new thing. So, I didn't invent the idea of computing maximum matchings using some kind of flow problem. What I will observe is there actually are a variety of ways of performing this construction, turning our bipartite graph into a flow network. I'm going to use this one for the entire lecture. It's not the only solution, nor is it necessarily the most convenient one. It's just convenient for me, given the theorems that I'm going to prove in a minute. If you look at other sources, and I'll include some of them in the references, there are sources, for example, that do not assign a capacity of 1 to these edges in the middle, the edges between X and Y. There are some sources that even assign a capacity of infinity to those edges. But we don't want to talk about infinity just yet. And also, one of the reasons I like using a capacity of 1 here is that later on, one of the theorems that we come up with will just be a lot easier to employ if we can guarantee that every single edge in our graph has a capacity of 1. So there are lots of ways of doing this construction, and like a lot of the algorithms and constructions we've seen in this course, just because there are lots of ways of doing it doesn't mean you should automatically be suspicious of any of them. Just that the structure of the proofs that one has to write looks a little bit different depending on the nature of their construction. Okay, if I go and find a maximum flow for this constructed flow network, you can observe that if I look only at the edges that this network shares with my original bipartite graph, the edges between X and Y, because of course the edges over here are all made up, as are the ones over here, if I look at only the edges in the middle, notice that what I end up with, the saturated edges, which I will shade in blue here, the edges with 1 unit of flow, those actually correspond to a matching of size 4. Now, whether or not that's a maximum matching is a different question, and in fact, this one example doesn't even prove that we're always going to get this result. But it certainly looks promising. It certainly looks like these constraints I've been able to impose on the flow network are getting me what I want, a collection of edges that do not share endpoints. Now, if we try the same construction on this other bipartite graph, so I start with this undirected bipartite graph, and then I attach a source vertex over on the left, a sync vertex on the right, and observe that one characteristic of this particular construction is, unlike general flow networks, it's actually the case that there are no directed cycles in this graph. There's no way for flow to travel around in a circle no matter what. It is possible, of course, that flow might one day have to travel backwards along an edge, for all I know, because that's the way augmenting paths work, but in general, if I look at a flow assignment, a feasible flow, all flow starts at S and travels strictly to the right until it reaches T. So basically the question is, can I prove that if I generate one of these flow networks out of a bipartite graph, and then I compute any maximum flow of that flow network, that the edges with non-zero flow in the resulting maximum flow correspond to a maximum matching? Now, this is a bit of a weasel word. Why am I saying non-zero? You'll observe that if I look at the edges in the middle, or indeed any of the edges in the graph, that all of the edges have either 1 unit of flow or 0 units of flow. That's what we're used to when we deal with flow networks with integer capacities. Something that we haven't officially proved, and I actually will prove it in a few minutes just to tie up that loose end. So why am I saying non-zero flow? Well, I guess it's fewer words, it's a shorter sentence, less of a mouthful than if I had to say edges with a flow that is valued at 1, or something like that. So the question is it true that if I look at any maximum flow and I pick out the edges that have any flow running along them, that I end up with a matching? And it turns out that the answer is actually no, because of this situation. So here is a maximum flow. You can observe that this flow has value 3, just like the flow I had on the previous slide. And I guess you could try out the Ford-Fulkerson algorithm to verify that it would get stuck here and not be able to find an augmenting path, meaning that the flow indeed is maximum, as we proved last time. And so this flow is maximum, although it looks rather strange. Now, it turns out, in fact, that the reason the flow looks so strange is because this is a flow that the Ford-Fulkerson algorithm would never produce. So we haven't seen a flow like this in the wild before, because the flows we've been working with have been ones produced by the Ford-Fulkerson algorithm or one of its variants. But this is still feasible. All of the constraints are still being met. If you look at any vertex, flow is being conserved. It's weird. It's very strange that I send one unit of flow from S to X, and then I diffuse it among 3 destinations from X, but I'm allowed to do that if I want to. And we also know that the Max-Flow Min-Cut Theorem applies to all maximum flows, not just to ones produced by the Ford-Fulkerson algorithm. Although the Ford-Fulkerson algorithm is something we used as part of the proof, the Max-Flow Min-Cut Theorem applies in general. I can actually even eyeball a minimum cut of this flow, so corresponding to this flow. So for example, if I look at this cut here, you can observe that all of the edges crossing from the set S to the outside world are saturated, and that the total capacity of the cut is 3. Okay, so I have this weird looking flow here, which pretty much roundly disproves what I was trying to get at with my question, which is maybe every maximum flow corresponds to a maximum matching. But it doesn't, because if I look at the edges that receive non-zero flow here, they obviously aren't a matching. They're every single edge in the bipartite graph, and there's tons of shared endpoints. There's also no obvious way to distill this set of edges down into a matching. I mean, if I take only the edges that have flow 1, well then I take no edges at all, because no edges across between X and Y have flow value 1. If I take only the edges with flow value greater than or equal to 0.5, then I don't get a matching. So it's unclear what to do in this case. So this certainly disproves that any maximum flow corresponds to a maximum matching. But we can prove that flows like this, for this particular type of network, will never be produced by the Ford-Fulkerson algorithm or its variants. And that is due to a property that we actually have been leveraging. So even 2 lectures ago, when I mentioned that the Ford-Fulkerson algorithm always terminates as long as the capacities of each edge are integers, there's a fact that we didn't prove back then that I guess I should prove now, because I need to employ it for the sake of this construction. And by doing this, we are also going to finally tie up that loose end. Just in case you were skeptical about me saying that important thing without proving it, well, here's the proof you were looking for all along. And it's called the Integrality Theorem, or the Integral Flow Theorem. And it says that if G is some flow network in which the capacity of every edge is an integer, then at every step of the Ford-Fulkerson algorithm, the flow along every edge will also be an integer. In other words, after every augmentation, the flow along every edge will be an integer. And that, of course, means if you extrapolate that outwards, that means when the algorithm eventually finishes, the flow that we come up with will be integer valued. So there will not be any 0.5s across edges, as long as we know going into it that the capacity of every edge is an integer. Now, even though I just said all this grandiose stuff about how it's important that I finally provide a proof, I'm actually not going to give you the full proof. I will, however, observe that this is exactly the type of theorem that could make a great exam question to write the proof for. I also think that the proof itself, the formal proof, isn't really that complicated once you know the basic insight behind it. So I'm going to go over a sketch at a high level of how the proof might work. Now, there might be more than one way to do this. The way I might recommend doing is to use induction on the number of augmentations, because we know that at the beginning of the algorithm, the flow that we start with, the all zero flow, is clearly going to have integer values of f, because at the beginning f of uv is equal to 0 for every edge uv. Okay, so at the beginning of the algorithm, the base case for induction pretty much, the value of the flow across any edge is 0, which is an integer. Okay, so then our induction hypothesis would be something like, suppose that the flow across every edge is an integer after I augmentations, and consider what happens after augmentation I plus 1. So we know that if there is another augmentation that happens, it's because we found an augmenting path. We know that if the amount of flow across a particular edge is an integer and the capacity is an integer, well then the residual capacity has to be an integer as well. Because the way that we define residual capacity basically amounts to, it's either this. So if f of vu is an integer, then negative f of vu is clearly going to be an integer as well. And the other term that contributes to residual capacity is the capacity of the forwards edge minus the flow along the forwards edge. And clearly if c and f are both integers going into this, the residual capacity will be an integer as well. We also know that the amount of flow that we actually push along our augmenting path, which is this value here, this cf of p is just the minimum value of the residual capacity of the edges along P. So we've got CF, it's the minimum of CF of UV for UV along P. Okay, so what that's telling us is that the amount of flow that we push at each step of the Ford-Fulkerson algorithm is going to be an integer as well, which means if the amount of flow along each edge was an integer before the augmentation and we push an integer amount of flow along the edge, well, then the amount of flow along the edge is an integer after the augmentation. So I think really that is pretty much all there is to the proof, although the problem of writing the proof out in full might be something that you want to practice in the near future. Okay, so now that we have the integrality theorem, we can state a couple of other results, some of which are relevant to our immediate situation, and the other one is just something that I guess a loose end we ought to tie up from a couple of lectures ago. So the first one is that loose end. So if G is a flow network and all of the capacities are integers, then the basic Ford-Fulkerson algorithm, the one where augmenting paths are chosen by any means you want, BFS, DFS, or any other traversal that you can come up with, that algorithm always terminates. In other words, we don't have to worry about it entering an infinite loop, because I was able to say and justify intuitively that we didn't have that situation a couple of lectures ago. We now have that formalized using the integrality theorem. So the integrality theorem is implying that because the capacity of the augmenting path at each step has to be an integer, and we know that because it's an augmenting path, its capacity has to be greater than 0, well, the next integer up from 0 is 1, so the capacity of the path has to be at least 1. Which means if we consider the maximum flow that we're building up to, we'll call it F star, the maximum number of augmentations has to be at most the value of F star, because if we add at least 1 unit of flow at each step, the maximum number of times we can add 1 unit before we reach this number is this number itself. Okay, so that's how we now know that even if we don't use the Edmonds-Karp algorithm, the Ford-Fulkerson algorithm, the basic version where the traversal is unspecified, that will always terminate. Okay, and the other implication of the integrality theorem, coupled with the fact that we now know that the Ford-Fulkerson algorithm always terminates, is that if you have a flow network where every capacity is an integer, then there has to exist a maximum flow where the flow along every edge is an integer-valued maximum flow. And the reason for that is that by the integrality theorem, the Ford-Fulkerson algorithm puts an integer-valued flow along every edge at every step, and by the corollary we just had, the Ford-Fulkerson algorithm always terminates. It always reaches a maximum flow. We've already proven that if the algorithm terminates, the flow it's come up with is maximum. And so therefore, there must exist a maximum flow where the value of f for every single edge is an integer. So we can use that result to prove that a maximum matching in a bipartite graph can be computed using our flow network construction if we make sure that the flow that we're working from is an integer-valued flow. In other words, if we compute our maximum flow with the Ford-Fulkerson algorithm or one of its variants, like the Edmonds-Karp algorithm, then we can take that flow and use it to create a maximum matching. Now, before I get to the theorem, I want to formalize my construction. Okay, so what I'm going to call this for the rest of the lecture is the flow network construction for bipartite matchings. So if later in the lecture I'm going to refer to the flow network construction and refer back to slide 46, it is referring to this. Now, nothing is really new on this slide. This is just a way of formalizing the construction that we already saw, where I have some bipartite graph, and I take the bipartition, so I take x and y, and then I add a source vertex S, and I add a sink vertex T. Okay, so let G be a bipartite graph and let X, Y be a bipartition. As I mentioned earlier, and as we saw back in lecture 27, if a graph is bipartite, a bipartition can be computed relatively easily. Now, let's define a flow network. We're going to call it H, and its vertex set will be all of the vertices of G plus a new source vertex and a new sink vertex. And then we'll add the following edges. Okay, so for every edge in the original graph G, where without loss of generality, so the edge is the edge UV, let's just assume that U is on the X side and V is on the Y side. And that might sound a bit creepy, like it might sound like I shouldn't be allowed to do that. So we know that there is a bipartition, and we know that every edge crosses over between X and Y. We also know that the original graph G is undirected, which means the edge UV, well, I should draw my characters more distinctly, the edge UV and the edge VU are considered to be exactly the same thing. All I'm really saying here, and the reason I'm being so clear about this is I'm going to use this over and over again during the next few proofs. What I'm really saying here is, okay, look at some edge in EG. And then we know that one endpoint's in X and one endpoint's in Y, so call the endpoint in X U and the endpoint in Y V, just to make our lives easier. Okay, so for each of those edges, we're going to add an edge from U to V in our flow network H, because H, of course, is a directed graph, so it has direct directed edges. So of course, as usual, I want to have my source vertex, and then it's going to have edges that go from it into x, edges go from x into y, and then edges go from y over to my sink vertex t. So for every edge between x and y, I add an edge pointing from the vertex in x to the vertex in y. Then I add an edge from the source vertex s to the vertex u for every vertex u in x. And then I add edges from every vertex v in y to the sink vertex t. And all of the edges I create in this construction have capacity 1. Okay, so that is our flow network construction. Now that we have that formalized, I can state the theorem that we want to prove. So if f is an integer-valued maximum flow over h, something that we now know must exist because we can easily show that the capacities of every edge in my flow network are integers, they're all just 1. If f is an integer-valued maximum flow, then the matching created I shouldn't say matching just yet. The set M consisting of all of the edges in the integer valued maximum flow whose flow value is equal to 1, that is a maximum matching of G, of the original bipartite graph G, and the size of that matching is equal to the value of that maximum flow. Okay, so at the moment, all we know, because we haven't proven the theorem yet, is that M is the set of all these blue edges, all the edges crossing from X into Y, where the flow over the edge is equal to 1 and not 0. Now, to prove the theorem, well, there are a few ways to do this. The way I'm going to choose to do this is I'm going to begin by showing that M is a matching. So in other words, there are no two edges that share an endpoint. Then I'm going to show that no larger matching can exist, which of course means that M is a maximum matching. And actually in the middle of that, I'm also going to prove this point here, because we actually have to say this. We actually have to assert that this point actually holds. The size of the matching, the number of edges in it, is equal to the value of the flow. Although there are some sources that don't bother proving that step because they can argue that it's sort of obvious or something. What they can do is basically say, let's take a look at the value of the flow across this particular ST cut. So basically, if I make an ST cut that divides the graph down the middle, so I look at the flow between X union the source vertex S and Y union the sink vertex T, that's obviously going to equal the value of my entire flow F because of something we saw in the last lecture, and it's also going to equal the size of my matching M, basically because of the way the matching is defined. Every edge across from X to Y either has flow 0 or flow 1. All the edges with flow 1 are clearly in the matching M. So I'm going to prove that myself. I'm going to use very similar logic, but I'm not just going to sketch it out like this. Okay, so claim number 1. The set M is in fact a matching of G. Okay, so by the definition of M, every edge is an edge of the original bipartite graph G. Now what I mean by that basically is that notice that in our flow network construction, we have a bunch of edges that weren't part of the original graph. Like these edges over here weren't part of the original graph, neither were these here. So the very first thing, the 0th thing I have to show to justify the claim that M is in fact a matching is that all of the edges that I've put inside of M are actually edges in the original graph, because it's not a matching if it contains edges that don't exist. However, because of the way that I define M and the way that I define my flow network, all of the edges in my flow network bridging between X and Y are real edges of the original graph. Okay, so there's that. So every edge in M is an edge of the original bipartite graph. Additionally, since I have an integer valued flow F and all of the edges of H have capacity 1, for any edge in H, the flow across the edge has to be either 0 or 1. It must be an integer, and the only integers available are 0 or 1 if the capacity of the edge is 1. Okay, so therefore, all of the edges in the original graph that are not in my set M, my purported matching, they must have flow 0, because M contains all of the edges in the original graph between X and Y that have flow 1 across them. Okay, so now let's take a look at various cases. So if I take a look at a vertex in X, so on the left-hand side of the bipartition, suppose that the flow from the source vertex S to my vertex U here is equal to 0. Well, that means that by conservation of flow, there can't be any flow leaving the vertex U either. The only edge inbound to vertex U comes from the source vertex S. If there is no flow coming in, there can be no flow going out. Okay. But on the other hand, if the amount of flow coming in is equal to 1, the only other option, then by conservation of flow, 1 unit of flow must leave vertex U. But because I'm only allowed to push either 0 or 1 units along each edge, only one edge outbound from U can have flow along it. Every edge has to have flow 0 except for a single edge to some vertex V in Y that has 1 unit of flow. It's impossible in an integer valued flow, for example, to have a case where you've got 0.5 units here and 0.5 units here. What this is telling me is that if I have some edge attached to vertex U with flow across it, U will never be incident to any other edge with flow across it. In other words, there will never be any second edge in M that is incident to U. Okay, I'm now going to show basically the same thing for vertices over here in Y. If I look at a vertex in Y and I notice that 0 units of flow are leaving this vertex V, well then of course by conservation of flow, 0 units of flow can be entering the vertex V. So certainly there's no way that vertex V is incident to 2 edges in M. On the other hand, if 1 unit of flow is leaving vertex V, there can be exactly 1 edge that has flow inbound to V, because otherwise I would need to have fractional flows which are not allowed, which means there is no way that there are 2 edges that were selected for M that are both incident to V. And therefore I now know that no vertex in X and no vertex in Y is incident to more than 1 edge of M, so M is a matching of G. We don't yet know that M is a maximum matching, but it is a matching. Okay, next point. The number of edges in M is equal to the value of the flow, the value of this maximum flow that I use to construct M. Okay, so the way I'm going to prove that is I'm going to start with the definition of maximum flow. Or the definition of the value of a flow. So the value of a flow is defined to be the net flow leaving the source vertex S. But in this case, we happen to know, because of our construction, that there actually are no edges that enter the source vertex S. Normally, the value of a flow is specified with a more complicated expression that includes the possibility that flow is re-entering the source vertex. Because we know that there are no edges whose endpoint is the source vertex, we can simplify the value of the flow, the expression for that, to this, a single sum, which is simply the sum of the flow across every edge from S to somewhere else. Because we know from our construction that all of the edges leaving S go into a vertex in X, we can just define the sum as being across only those vertices. Okay. So by conservation of flow, if I take my source vertex S and I notice that flow is proceeding from S to some vertex U, the amount of flow entering that vertex must equal the amount of flow leaving that vertex. That's just basic conservation of flow. So what I can do there is I can say, okay, that means the total amount of flow leaving vertex S has to equal the total amount of flow across between all of the vertices in X and all of the vertices in Y, if I just sum that up. And then I realize that if I look at edges between X and Y, there are some edges that have 0 flow across them and some edges that have 1 unit of flow across them. The edges that have 1 unit of flow are exactly the edges that I added to M. The edges with 0 units of flow are completely irrelevant to me. They contribute nothing to the total flow leaving S. Okay, so the total amount of flow traveling from X to Y is just going to be equal to the total amount of flow traveling across edges that are in M. And of course, because every edge in M has exactly 1 unit of flow, this sum is equal to this sum. And if I just make a sum of ones, where the number of terms is equal to the number of things in M, well, really what I'm doing here, so if this is size of M, well, then I'm just computing the size of M. Okay, so what I was able to show is that the value of my maximum flow is equal to the size of the matching that I constructed. So we know from claim 1 by now that it is a matching. Okay, claim 3. No matching of G has a size larger than the size of my set M. Okay, so the way I'm going to do this is I'm going to suppose that such a matching exists. Suppose there was a matching that was bigger than the matching M that I've just constructed. And what I'm basically going to do is show that if this is true, I can create a flow whose value is larger than the maximum flow F that I saw earlier. And of course that makes no sense because F is a maximum flow. All right, so suppose that M prime is some matching whose size is larger than M. I'm going to construct a new flow F prime as follows. I begin by setting every single edge to have 0 units of flow. And then I proceed by, if there is an edge that appears in M prime, so of course we know that because M prime is a matching of the original graph G, every edge in M prime has to connect between X and Y. Okay, so for each edge in M prime, where without loss of generality, we assume that the endpoint in X is called U and the endpoint in Y is called V, let's just route one unit of flow all the way from the source vertex to the sink vertex. So I send one unit from S to U, from U to V, and from V to T. Now, because M prime is a matching, I know that there is no way that the vertex U has two edges incident to it that are both in M. That would be impossible because then M prime wouldn't be a matching. And one reason why it's important to observe that not only is for this next segment of the proof, but also because this trick I'm using where I send one unit all the way from S to T across the edge UV, that wouldn't work if it turns out that multiple edges could be incident to U and still appear inside the matching. Because what would happen is basically I have one unit entering vertex U and two units leaving, which wouldn't make any sense. So because of the fact that it's a matching, I know that if there's some edge incident to U in the matching, there will be no others. And therefore, if I send one unit from S to U, from U to V, and from V to T, with this assignment here, that flow will in fact be conserved. Okay, so additionally, since M prime is a matching, no vertex in X can be incident to two edges in M prime. Therefore, basically by the same logic as claim 2, if I look at the value of my new flow F prime, or actually I haven't yet proven that F prime is a feasible flow, but if I try to compute its value is going to be equal to this. It's going to be equal to, for every edge UV and M prime, I'm pushing flow from S to U, so that's a consequence of this line here. And by the same logic as claim 2, that is just equal to the value of F prime across all edges UV that are in M prime, which is just equal to the size of M prime. So what I've shown is that the value of F prime is equal to the size of M prime. Which means if I can show that F prime is a feasible flow, then we have that F prime has a larger value than my maximum flow F, which clearly isn't allowed to happen, and that would give us a contradiction. All I have to do now is show that F prime is feasible. Okay, so the first thing, to assert feasibility, I have to verify that F prime satisfies the edge capacity constraints. And of course, we know that every edge in the graph has capacity 1. So it's pretty easy to show that F prime satisfies that, because the only flow we pushed into F prime are these flows of value 1. Okay, so because all edges have capacity 1, there's no way any edge's capacity could be exceeded. Okay, so the flow F prime satisfies the edge capacity constraints. Additionally, what we have to show is that flow is conserved. But it turns out it is. So because of this trick, where whenever I wanted to assign flow in my flow F prime, I pushed the flow all the way through the graph in one swoop. So I went from S to U to V to T. That means that flow is being conserved. The unit of flow that enters U here, exits U here, enters V, and then exits V and reaches T. So flow is conserved. Therefore, F prime is a feasible integer-valued flow. And since the value of F prime equals the size of M prime, and the size of M prime is greater than the size of M, which is equal to the value of F, the original flow F wasn't maximum, because I just produced a larger one. That's obviously a contradiction. And so I rewind back to the last assumption I made, and it was this one. Suppose there does exist a larger matching. Well, it looks like that's impossible. And therefore, claim 3 holds. No matching of G has size larger than the matching M. And I'm ready to prove my theorem. All I have to do is combine together those 3 claims. So remember that my theorem was, if you give me an integer-valued maximum flow using my flow network construction, then the set M, which simply consists of all of the edges where one unit of flow is being passed from some vertex in X to some vertex in Y, that is a maximum matching whose size is equal to the value of my maximum flow. So by claim 1, M is a matching. By claim 2, the size of the matching equals the value of the maximum flow, and by claim 3, there cannot be a larger matching, which means M is a maximum matching, and its size is equal to the value of F. Okay, an obvious corollary of that, since we know that we can compute an integer-valued maximum flow in polynomial time, that means we can now compute a maximum matching of our bipartite graph in polynomial time as well. And it's true that we could use the Edmonds-Karp algorithm for this. So, of course, the Edmonds-Karp, as a variant of the Ford-Fulkerson algorithm, the Edmonds-Karp algorithm will compute integer-valued flows if the capacities of all edges are integers. And, of course, that is polynomial. It actually turns out that because the structure of this flow network is very specific, it isn't as general as the networks we saw last time, there are specialized algorithms that do run faster than the Edmonds-Karp algorithm. So we can just leave it at the point that we can compute maximum matchings in polynomial time, but there are, in fact, very very fast ways of doing it. So one example of such an algorithm is the Hopcroft-Karp-Karzanov algorithm, which can find a maximum matching in this amount of time, which is pretty good. What's sort of neat about this is you can see the name carp in there. That's the same carp as Edmonds carp. And I observed last time that both Edmonds carp and Dinitz, so the pair of Edmonds and carp and Dinitz separately were the ones to come up with a polynomial time variant of the Ford-Fulkerson algorithm that used BFS to find augmenting paths. The reason why we didn't call the whole algorithm Edmonds-Karp-Dinitz or Dinitz-Edmonds-Karp is because Dinitz's algorithm was a little bit different. It did its bookkeeping differently and managed to get a better running time overall, although ultimately it found its augmenting paths using BFS. It turns out that Dinitz's approach could be adapted for other purposes to produce nice fast algorithms, including the Hopcroft-Karp-Karzanov algorithm, which can find a maximum matching much faster than Edmonds-Karp. So it's neat that Karp was involved in that. Karp was involved in adapting Dinitz's algorithm for that purpose. So what we've just shown is that because I was able to model the refreshment problem using a bipartite graph, and I determined that what I wanted was to find a matching in that graph, a maximum matching, a set of refreshments where I do not repeat types or flavors, we have shown that it's possible to choose a maximum size collection of refreshments without repeated flavors or types in polynomial time using an algorithm like Edmonds-Karp. And it turns out that a maximum matching of this bipartite graph corresponding to my refreshment problem has size 5, which means it isn't possible to select 6 items where each item has a distinct flavor and type from all of the other items. So unfortunately, if I do want to have 6 frozen refreshments, I am going to have to repeat at least one flavor or type. On the other hand, I've been thinking a bit about that problem since I brought it up a few minutes ago, and I think, I might have had the wrong idea. So I've been thinking a bit about this. I've listed, for example, freezies come in raspberry, and so does frozen yogurt, and so do snow cones and sorbet and popsicles. And I've thought a lot about this, and I've realized that, a raspberry freezie really isn't the same as raspberry frozen yogurt. In fact, I'm aware of the fact that a freezie actually comes in blue raspberry, whereas frozen yogurt typically comes in traditional red raspberry. So the question is raspberry frozen yogurt, is that really a comparable raspberry experience to having a raspberry freezie? I don't think so. Maybe I've had the wrong approach all along. It's one thing to minimize the amount of sugar that I consume, but it does feel like I shouldn't deprive myself of the full sensory experience of enjoying raspberry in all of its forms. So maybe avoiding repeated types or flavors isn't really what I wanted to do. I want to experience all of the different variants of each flavor. I want to know the difference between a raspberry freezie and raspberry frozen yogurt. So I think I want to go in the other direction. Maybe I want to try out every possible combination of type and flavor. I want to try a raspberry frozen yogurt and a raspberry freezie and a raspberry snow cone and a raspberry sorbet. But I also want to avoid, breaking the bank. It does seem like I'd feel pretty guilty if I'm spending a huge amount of my budget on refreshing frozen snacks. So I'm not going to go buy them individually, obviously. If I walk into the corner store and try and buy myself 18 frozen novelties, people are going to give me funny looks and I'll be embarrassed. So of course, like any other self-respecting person, I'm going to go to the grocery store and buy them in bulk. But if I do this, they're only sold in these assortments. You can't buy individual ones. Instead, you could, for example, buy the popsicle assortment, which has every possible flavor of popsicle, or the snow cone assortment with every possible flavor of snow cone. Now, wait a minute. How am I able to buy a bunch of already produced snow cones in the frozen section? Don't worry about that. That's not germane to this problem. I shop at a special grocery store that only caters to graph theorists. It's all right. I could also buy assortments of a particular flavor. So I can buy assortments of a particular type, like every kind of frozen yogurt, every kind of popsicle, or I can buy all of the different grape flavored things, or all of the different raspberry flavored things. And so what I want is to enjoy one novelty of each combination of type and flavor. One way of doing this would be to buy every assortment by type. So I buy the assortment of every single type, which would indeed give me one instance of each type and flavor combination. I would buy 6 assortments in this case. Or if I wanted to, alternatively, I could buy every assortment of a particular flavor. So I could buy all 6 assortments corresponding to collections of particular flavors. That again would require me to buy 6 assortments. I mentioned a minute ago that, my sugar consumption is one thing, but I also feel sort of guilty if I spend too much money on junk food. So I'm wondering, is it really necessary to buy 6 assortments to get one of each combination of type and flavor? And it actually turns out that the answer is no. If I buy this collection of 5 assortments, the frozen yogurt assortment, the popsicle assortment, and the assortments of grape, orange, and raspberry, I do actually get at least one of each item. So for example, if I want a grape freezy, I can get that from the grape assortment. So I will have a grape freezy. If I want a raspberry freezy, don't worry, that's coming in the raspberry assortment. If I want an orange slushy, I'm getting that in the orange assortment. Grape slushy, that's in the grape assortment. Orange snow cone, that's in the orange assortment. Raspberry snow cone, definitely getting that. Grape sorbet, raspberry sorbet, yep, getting both of those. So notice that I am in fact getting one of each type and flavor and a bit of a bonus. Notice that I'm actually getting a raspberry frozen yogurt twice. I'm not going to argue with that. And I'm actually getting a raspberry popsicle and a couple of other things twice as well. I actually get a bit of duplication. So I'm able to buy less than 6 assortments. I actually get more than what I want. Okay, so the slides agree with me. The slides are just listing the assortments that I've highlighted here. And so the question then is, okay, I was able to get one of each combination by buying only 5 assortments. Is there a way that I could buy only 4 of them, such that I still get one of each combination of type and flavor? And we can actually use bipartite graphs for this as well. We have to talk about something called a vertex cover. So a vertex cover in any graph, not just a bipartite one, is a subset of the vertices, such that every single edge in my graph has at least one of its endpoints in the set C. So at least one of the 2 vertices at each end of an edge is in my vertex cover. And if we stare at this set for a minute, we can observe that indeed it is a vertex cover. Let's just pick an edge. So here is an edge here. Notice that one of its endpoints is in the vertex cover. There's no requirement, unlike a matching, that the vertex cover not be covering both endpoints of an edge. So of course, this edge here actually has both of its endpoints in the vertex cover. A vertex cover is just some collection of vertices such that at least one endpoint of each edge is in the vertex cover. Is this a vertex cover of the graph that's shown? Turns out that the answer is no, because this edge here has neither of its 2 endpoints highlighted. So the blue vertices are the vertex cover, and none of them covers this edge here. One thing I can observe is that if I have a bipartite graph with a particular bipartition, then if I just choose all of the vertices on one side of the bipartition, so for example, all vertices in X or all vertices in Y, that collection would be a vertex cover. So if I look at only the set X, that will always comprise a vertex cover because every edge must have one endpoint in X. And in fact, if I'm especially lazy, I could just choose the entire vertex set as my vertex cover. Now, these 2 examples might sort of hint that vertex covers fundamentally are something that is more challenging to make smaller. Earlier, we saw with matchings that it's easy to make small matchings, but a bit more challenging to make large ones. Here, we're seeing that it's easy to make a big vertex cover, but it might become a little bit dicey if I want to make my vertex covers smaller. So for example, here, I was able to make a vertex cover of size 4. Can I make one of size 3 for this graph? So a minimum vertex cover is a vertex cover of minimum size. It turns out for the graph shown here, the size of a minimum vertex cover happens to be 4. There is no vertex cover for this graph that contains only 3 vertices. If you have only 3 vertices, there will always be at least one edge that is not covered. Now, an odd coincidence is that if I go looking for maximum matchings of this graph, the maximum matching also has size 4. That's sort of weird. And if I look at a graph, some other bipartite graph, here's another bipartite graph, the minimum vertex cover has size 4, and so does a maximum matching. Another weird coincidence. That coincidence holds on this graph as well. So on this graph, a minimum vertex cover has size 3, and a maximum matching also has size 3. And that's true here as well. It does look as if on all of the examples we've seen, the size of a minimum vertex cover also happens to equal the size of a maximum matching. Now sure, I could make smaller matchings than this, and I could make larger vertex covers than this, but the smallest possible vertex cover happens to have the same size as the largest possible matching. And so I guess the natural question is it possible that a minimum vertex cover and a maximum matching always have the same size? And the answer, it turns out, is yes. And we can demonstrate this. We can actually find vertex covers of bipartite graphs using the same flow network construction as earlier. So I told you I was going to do this. If we think of the flow network construction from earlier, the one on slide 46, we can actually use the same construction to find vertex covers that we use to find maximum matchings. We just have to look at something else about our related to our flow problem. Now, in this part of the lecture, so I'm going to need to draw a bunch of, draw all over these diagrams. So we already know with this flow network construction, if we use the Ford-Fulkerson algorithm to compute an integer-valued maximum flow, that every single edge, once we have that maximum flow, every edge will either have 1 unit of flow or 0 units of flow. And I've adopted the convention of when the edge has 1 unit of flow, I color it blue. When the edge has 0 units of flow, I don't color it in at all. It looks like a normal edge. I'm going to maintain that convention, and I'm going to stop drawing the flow amount across each edge. So I'm just going to draw it like this. But we interpret the blue edges as having 1 out of 1, and the, non-blue edges as having 0 out of 1, just to clean the diagram up because it's about to get a bit messy otherwise. All right, let's take a look at a minimum cut of this network. So I've computed an integer-valued maximum flow, and I know from what we've already proven that if I look at the edges between x and y, those that have any flow across them, the blue edges, comprise a maximum matching. If I go and get a minimum cut of the flow network, and this is a specific minimum cut that we've created using the process we described in the previous lecture, where what I do is I define the set S to contain all vertices reachable from my source vertex in the residual network. If I look at that minimum cut, and then I compare it to a particular minimum vertex cover, notice a sort of neat pattern. All of the vertices in X that aren't in my set S are in the vertex cover. All of the vertices in Y that are in my set S are in the vertex cover as well. Before we go forward though, now that we have this minimum cut, just to remind ourselves what minimum cuts look like. So of course, the set S is the stuff shaded in green, and the set T is everything that isn't shaded, as per the convention I established in the previous lecture. Wait a minute, these vertices that I've shaded in red here, notice how the edge from S to those vertices is saturated. So I just said earlier that the set S consisted of all vertices that were reachable from my source vertex S in the residual network. Isn't that an error? Why are these two vertices in the set S in that case? So think about that. It's not an error. It turns out they're supposed to be there, but even I got caught off guard by this while proofreading the slides. But it turns out it's legit. Just remind yourself why it could be the case that these vertices are included, even though the direct path from vertex S is saturated. It turns out they're still reachable. Okay, so the vertex cover contains all vertices in the intersection of X and T, so that would be this stuff up here, along with all the vertices in the intersection of Y and S. If I do the same thing with all the other graphs we've looked at, I notice that the same property holds. So if I look at this flow network construction here, here are the vertices in Y intersect S, and here are the vertices in X intersect T, and together they comprise a minimum vertex cover. If I take a look at this graph here, it looks a bit more messy, but if I take a look at the vertices, so these two vertices here are the vertices in Y intersect S. They're both shaded in green and over on the right, and here are the vertices in X intersect T, and together they comprise a minimum vertex cover. If I look at this graph here, it turns out the same property holds, although it's a little bit unusual. So here the set S is just equal to the source vertex. But that does mean that because the set T is then equal to everything else, my minimum vertex cover does consist of everything in X intersect T, and it happens that in this case, Y intersect S is just the empty set. So it looks as if in all cases, I've observed that the minimum vertex cover equals the intersection of X and T, so the unshaded vertices over on the left, as well as the shaded vertices over on the right. And we can prove this. We don't know in general that this holds for all graphs until we prove it, but we can prove it. So our theorem is actually a bit of a parallel to the theorem we proved earlier about maximum matchings. We're actually going to use the same integer-valued maximum flow over the same flow network construction. We're now going to evaluate this minimum cut ST as a way of constructing our vertex cover. Okay, so let G be a bipartite graph, and let this be its bipartition, and then let H be the flow network corresponding to G, so using the construction we've been using all along. Let F be an integer-valued maximum flow, as we used in the earlier theorem, and finally, define a minimum cut, ST. The particular one I'm going to use is the one that we used in the last lecture, which is the set of all vertices, so S is the set of all vertices reachable from my source vertex in the residual network with respect respect to the maximum flow that I'm working with. Under those circumstances, the set C, which is the intersection of x and t union the intersection of y and s, is a minimum vertex cover of G with this size. The size of the vertex cover equals the capacity of the minimum cut. Now, I'm sure you've observed it by the long-winded way I have to read this thing out. This is not a very easy thing to think about visually. I have a lot of diagrams in the upcoming slides to make it a little bit easier to understand. The key thing to understand about the way I'm defining the vertex cover is it's all of the vertices in X that aren't part of S, so the unshaded stuff on the left, and all the vertices in Y that are part of S, so the shaded things on the right. That's all we really have to worry about as far as visualizing this vertex cover. So similar to our proof for maximum matchings, the way we're going to prove this is by first, so I've defined this set C, and I've claimed it's a minimum vertex cover with this size. I'm just going to prove the different pieces of that as separate claims. I'm first going to prove that C, in fact, is a vertex cover, and then I'm going to show that there cannot be a smaller vertex cover. And then separately, sort of sandwiched between those two results, I'm going to prove the thing about the size. Okay, claim 1. The set C is a vertex cover of the graph G. Okay, so as I mentioned a minute ago, I'll use these diagrams to help illustrate what's going on. The set C is going to be the vertices not in S over on the left and the vertices in S over on the right. So let's take a look at some edge. So what I want to do is show that my set C, show that the shaded vertices comprise a vertex cover of my original bipartite graph. So of course, to do that, all I really have to do is to show that if I pick any edge from my original graph, one of its endpoints is in the set C. Let's consider some edge in my original graph, and let's assume as usual that U is the endpoint in the set X and V is the endpoint in the set Y. Okay, well, obviously, if U is in T, so if U is not shaded here, if it's part of my set T, well, then clearly, by definition, it's part of C, and therefore the edge is covered. Okay, so conversely, if V, which is an element of Y, if V is an element of S, well then V is an element of Y intersect S, which means it's part of my vertex cover C, and the edge is covered. Which means the only case I really have to worry about is a case where the vertex U is in S and the vertex V is in T, a case like this one. So suppose that we have that situation. Suppose that there is an edge connecting a vertex in S and X, a vertex in X minus C, basically, with a vertex in Y minus C. And you notice that neither U nor V is part of my vertex cover. So what I have to basically show is that this case cannot happen, that this is impossible. Okay, so what we're looking at here is we've got this edge from U to V, and one endpoint of the edge, the vertex U, is in S, and the other endpoint of the edge is not in S, it's in T. We know because of the way that we constructed our set S that has to mean that this edge is saturated for a couple of different reasons. One of them is if this edge weren't saturated, because I can reach the vertex U, if this edge had spare capacity, I'd be able to reach the vertex V, and that means V would be in S, which is a contradiction. Another way of thinking about it is, if we're looking at a minimum cut like this, all of the edges exiting the minimum cut, like this one, need to be saturated. And we illustrated why that was the case in the previous lecture. So one way or another, there is no way that any additional flow can travel along this edge. Okay, but by conservation of flow, so since there is flow along the edge UV, there has to be flow entering vertex U from the vertex S. Okay, so fair enough. And that means that there is no other way, so because obviously there's no way for flow to get to U any other way but via this edge here, because we're the ones who designed the flow network construction, and this is the only inbound edge to U. Additionally, because of integrality and conservation of flow, I know that all the other edges leaving vertex U have to have zero flow over them. There's no way they can have more flow, because how could they? There's only one unit entering vertex U. So what this is actually telling me is that there's no way for me to get from vertex S to vertex U in the residual network. The only two ways I can reach vertex U in the residual network are along this edge here, which I can't use because it's saturated, or via some other complicated path that involves walking backwards. But the only case where I could walk backwards along an edge like this is if it had some flow along it. And as I said a minute ago, because all the flow entering vertex U is going onwards to V, these two edges are completely depleted. There's no way to travel backwards along them. And that implies that U isn't reachable from the vertex S, that U is actually part of T, That's a contradiction because we earlier defined that U was part of the set S. Okay, so therefore this edge cannot exist. And therefore we either have the case where U is in T or V is in S, so one of U or V must be in C, and therefore edge UV must be covered. And so that means that our set C is a vertex cover of G. All right, claim 2. The size of our vertex cover, so we now know it's a vertex cover, the size of C is equal to the capacity of my minimum cut ST. And the way I'm going to assert this is basically by showing that all of the edges leaving, well actually I have diagrams for this reason. Okay, so every edge of H has capacity 1. Okay, so that's helpful. We also know that because of the fact that we're working with a minimum cut, so the cut ST is a minimum cut, and by a result I referred to a minute ago that we saw in the last lecture, every single edge that leaves the set S needs to be saturated for this to be a minimum cut. Okay, so since C is a vertex cover, basically because of what we just showed in claim number 1, it's impossible for any edge to connect a vertex here, so in the intersection of X intersect S, with Y intersect T, because due to the way that we've defined our vertex cover, this edge wouldn't be covered if it existed. So it's impossible, since we now know that C is a vertex cover, it's impossible for this edge to exist. Okay, so what does that tell us? It tells us that if I want to think of all the edges exiting the set S, the only edges that could exist are ones that go directly from the source vertex into, this would be X intersect T, or edges that go from some vertex in Y, and this would be the contents of Y intersect S, over to the sync vertex. Because there's no way, the other option would be edges like this, which we already saw cannot exist in this case. Okay, and so therefore the capacity of my cut is equal to the number of vertices in X intersect T plus the number of vertices in Y intersect S. Why am I saying number of vertices? Well, basically what I'm saying is each of the vertices in X intersect T has an edge going into it that's saturated. And we know that because the capacity of that edge is 1, this edge has to have 1 unit of flow. So the number of units of flow is just equal to the number of vertices, basically. Okay, the other thing I'll observe is the capacity of the cut is now this sum. But the size of my vertex cover is this number here, which is the size of a union. And it's not generally true that the size of A union B is equal to the size of A plus the size of B, unless both A and B happen to be disjoint. So this is only going to be true if A intersect B is equal to nothing. But that is true in this case. We know that X intersect T, that's this stuff here, and Y intersect S have to be disjoint because X and Y are disjoint. And therefore, that gives us what we need. The capacity of our cut equals this, which is equal to the size of the union of X intersect T and Y intersect S, which is exactly the size of our vertex cover. Okay, so we've now proven claim number 2. Okay, claim number 3. No vertex cover of G is smaller than the vertex cover I've just defined. So I've already been able to show that I have a vertex cover C and that its size is equal to the capacity of this ST cut. All I have to show now is that there is no smaller vertex cover. Because I have this result, what I can basically do is I can do the same trick I tried in the maximum matching case, where I construct another ST cut and show that it must have smaller capacity if there's a smaller vertex cover. And we know that that's impossible because we defined ST to be a minimum cut. So let's try that out. Suppose that C' is a vertex cover that is smaller than the vertex cover I have constructed. We are now going to construct our own ST cut, we'll call it S'T', as follows. Okay, well first I add the source vertex to S' and the sync vertex to T'. I'm going to add all vertices, so this is a weird way of framing this. It's sort of a backwards way of doing it. I'll read it out and then I'll just talk about the implications of it. What I'm going to do is add all the vertices in X minus C' to S', and all vertices in X intersect C' to T', and then similarly all vertices in Y intersect C' go into S', and all vertices in Y minus C' go to T'. I know that just seems like gibberish. What I'm doing with these bullet points is basically saying let S' equal this, let T' equal this. So if you stare at this for a minute, if we go on to the next slide, I can try and observe what I'm really trying to do here. What I'm arranging is basically to make it so that my ST cut allows me to basically make the same statement about C' that I made about my C earlier. In other words, what I'm saying basically is C' is equal to X intersect T' union Y intersect S'. And you can verify to yourself via some sort of fiddly, tedious set theory stuff enough that if I set up S prime and T prime to look like this, that C prime does indeed have this property. So that's really what's going on. Okay, and that means I can employ some of the logic I used in claims 1 and 2. So no edge can cross between the part of, between x minus c prime and y minus c prime, because by definition, the vertices in x minus c prime and y minus c prime aren't in c prime, which means if this edge exists, it wouldn't be covered, which means that c prime wouldn't be a vertex cover. But we just said c prime is a vertex cover. Okay, so that means that this edge cannot exist. Okay, and so then I can just use the same trick I used in claim 2 to demonstrate that the capacity of the cut that I just created, so C of S prime T prime, is equal to this, which is equal to the size of my vertex cover C prime. And we already know that the size of C prime is less than the size of T, and that the size of T is equal to the capacity of ST. And that's where we finally get our contradiction. So we started by saying that ST was a minimum cut, and I've now constructed a cut that has a smaller capacity. That's clearly a contradiction, and so therefore the C prime that I said was smaller than C, that can't exist. So as usual, I rewind back to my assumption, and my assumption was this thing. So I now know that this is impossible, and so no smaller vertex cover C prime can exist, and that means that my vertex cover C is a minimum vertex cover. So we'll go back to our theorem. There is our theorem from before, and we can write up the proof pretty easily by combining together our claims. So the basic statement of the theorem was that if I have this set here, this set C is a vertex cover, its size is equal to the capacity of a minimum cut, and it is a minimum vertex cover. Well, by claim 1, C is a vertex cover. By claim 2, the size of C is equal to the capacity of the cut, and by claim 3, no vertex cover can be smaller than C. So C must be a minimum vertex cover, and the theorem holds. All right, so an obvious corollary of that, because we know that we can find a minimum cut matching this description by running the Ford-Fulkerson algorithm. This is exactly the minimum cut that we defined in our proof of the Max-Flow Min-Cut Theorem. This means that a minimum vertex cover of a bipartite graph can be computed in polynomial time by finding a maximum flow and then computing the corresponding minimum cut. I guess I should say a maximum integer valued flow, although from the context that's sort of clear. All right. And so we've now used our flow network construction to find an efficient way to compute both maximum matchings and minimum vertex covers. I'd say that's a success, but actually the real result I've been building to wasn't any of those computational results. I want to state something absolutely profound about all bipartite graphs. And the result I'm going to state, despite the way I'm going to prove it, the result I'm going to state applies independent of any computational or algorithmic context. So I can say something very profound. And what I'm going to do, since I've now shown that the size of a maximum matching corresponds to the value of a maximum flow, and the size of a minimum vertex cover corresponds to the capacity of a minimum cut, I can bring out the Max-Flow Min-Cut Theorem. And it's really important to me to do this because, as I said last time, the Max-Flow Min-Cut Theorem is an incredibly big deal. But I had no ability last time to really justify that. I feel like this is just one of many results that help to emphasize what a big deal it really is. Okay, so here's the theorem. And this is a theorem that actually existed before the Max-Flow Min-Cut Theorem existed. So this is a theorem that can be proved via other means. If you've taken discrete math courses, you might have seen this theorem in other contexts. But I'll state it here, and we're going to prove it from scratch. Let G be any bipartite graph. The number of edges in a maximum matching is always equal to the number of vertices in a minimum vertex cover. All I really have to do is put together the pieces that we've been building for the entire lecture. If H is the flow network corresponding to G, then I choose some integer-valued maximum flow and minimum cut, although actually the theorem is going to hold whether or not F is integer-valued in this case, because there exists an integer-valued maximum flow. So although there might be other maximum flows, they're going to have the same flow value. So in fact, the theorem applies whether or not I choose integer-valued maximum flows, although I could do that in the proof if I wanted to. So choose some maximum flow and minimum cut. We know already that there is a maximum matching of G. Okay, the size operator isn't needed there. A maximum matching of G contains this number of edges, and a minimum vertex cover contains that number of vertices. And therefore, by the Max-Flow Min-Cut Theorem, by strong duality, we have the result that we're looking for. So I was able to use the Max-Flow Min-Cut Theorem by means of my flow network construction to prove that two apparently quite different problems, a problem involving maximizing a set of edges and a problem involving minimizing a set of vertices, that in fact the optimal solutions to those two problems always have the same size. That's a really big deal. What I've really proven is that the maximum matching problem, on bipartite graphs at least, is the dual of the minimum vertex cover problem. And that means if I have a solution to one problem, if I know the size of a minimum vertex cover, I also know the size of a maximum matching. And that this result, this duality result, is actually independent of computation. I don't need to compute anything to assert this result. The theorem tells me that for any bipartite graph, if you come up with a maximum matching of size 10, then a minimum vertex cover has size 10. Or alternatively, if you have a bipartite graph and you show me a matching you've found with size 17, and you also happen to find a vertex cover of size 17, it means your matching was maximum and your vertex cover was minimum. And that's independent of how you find them or whether you use an algorithm to do so. And so, of course, I can use these theoretical results we just proved to settle some of the open questions about my refreshment dilemma. So we already found a selection of 5 items that do not repeat types or flavors. I can have a grape freezy, a banana frozen yogurt, a cherry popsicle, an orange slushie, and a raspberry snow cone. I also found that it's possible if I buy 5 assortments, these 5 assortments, I can obtain at least one of each type and flavor combination. And we now know that the 5 items that don't repeat types or flavors, that corresponds to a maximum matching of this bipartite graph. And the 5 assortments that we can acquire to buy all possible items corresponds to a minimum vertex cover. And so, despite the fact those two problems, and when we frame them in an applied way, it's pretty clear those two problems do not sound like they're related. Certainly they both involve frozen refreshments, but choosing a large collection of frozen refreshments with no repetition and choosing a bunch of assortments I can buy at the store that give me every possibility do not sound like they are very related as problems or that they have the same solution. But by the duality of maximum matching and minimum vertex cover, we know that our solutions to both problems are optimal, and in general, this is going to apply no matter what set of refreshments, what types or flavors I am working with. No matter what particular refreshment dilemma I'm solving, the maximum number of refreshments I can choose with no repeated types or flavors will always equal the minimum number of assortments I can buy to get every possible type and flavor combination. And so, as I said, that applies, this is a generalized result that we were able to prove using the Max-Flow Min-Cut Theorem. Prove that 2 problems that seem pretty separate, a maximization problem involving edges and a minimization problem involving vertices, that deep down they are intricately and intimately related to each other. And if I find a solution to one, that implies aspects about the solution to the other. Now, I want to talk a bit more about matchings in general. I don't want to omit this. It actually turns out we're going to come back to some of this material later when we're done talking about flow networks, which will be a little while. But I want to at least observe that matchings can exist on graphs that aren't bipartite. So the flow network construction and the duality result that we proved only apply for bipartite graphs. Fundamentally, everything goes back to our earlier observation that with bipartite graphs, we can arrange the matching problem to look sort of like routing flow from left to right. That only works if you have a bipartition, though. If you don't have a bipartition, you can't guarantee all the results that we had. You can't actually use a maximum flow to compute a maximum matching in general. There might be algorithms that are based on similar ideas, but not based on the construction that we gave. And that means that the duality result that we proved also doesn't apply. So for general graphs, vertex covers can exist and maximum matchings can exist, but in general, a minimum vertex cover might be larger than a maximum matching. So in this graph here, this is a graph with 12 vertices, and it should be pretty clear. I mean, here's an odd cycle. It should be pretty clear that this graph is not bipartite. I was able to find for this graph a so-called perfect matching, a matching of size 6 that perfectly pairs up vertices. So there's no way that in this graph or any other graph on 12 vertices I will ever have a matching of more than 6 edges because there's no more vertices left. If I have a matching of 6 edges, all 12 vertices in the graph will be taken. So it's called a perfect matching because it's the maximum size any matching can ever be on a graph of this size. So a maximum matching has size 6. But it turns out that a minimum vertex cover actually has size 8. So there is no minimum vertex cover of size 6 on this graph. So our earlier result that applied to bipartite graphs clearly doesn't generalize to arbitrary non-bipartite graphs. And even worse, I guess, it turns out, our duality result from earlier was telling us not only is the size of a minimum vertex cover always equal to the size of a maximum matching, but it also tells us that it's pretty easy to compute either of them. I can compute a minimum vertex cover or a maximum matching, or in fact both of them in polynomial time using, for example, the Edmonds-Karp algorithm. but it turns out that the computational difficulty of the two problems doesn't appear to be the same, or at least we don't know it to be the same on general graphs. So there is no known polynomial time algorithm for the minimum vertex cover problem on general graphs. We can do it on bipartite graphs in polynomial time, but not in arbitrary non-bipartite graphs. Now, it's not currently known. So it's one of those problems where we don't know of a polynomial time algorithm, but we can't be sure that one doesn't exist. In fact, I can define a decision problem version of this to make this a bit more concrete. Consider this decision problem about vertex covers. You give me an undirected graph with n vertices and some value k. And I'm only supposed to tell you yes or no. Is there a vertex cover that has k or fewer vertices in it, of size at most k? So if so, I say true. If not, I say false. There is no polynomial time algorithm known to solve this problem. What's interesting, though, is that if I find a polynomial time algorithm to solve subset sum, I can use it to solve vertex cover with only a polynomial amount of extra work, and vice versa. It can be shown that any instance of the vertex cover decision problem can be converted to a subset sum problem in polynomial time, and vice versa. You give me a subset sum instance, there is, although it's a bit circuitous, a way of creating an equivalent vertex cover instance in polynomial time, which means if anybody ever discovers a polynomial time algorithm for vertex cover or a polynomial time algorithm for subset sum, then both problems can be solved in polynomial time. But we don't know of one just yet. Now, I will come back to this issue later, the idea that we have these problems that appear to be quite difficult and that they all seem to be equivalent to each other. We've seen that a few times in this course. I will talk about that, just not quite yet. So the vertex cover problem appears to be difficult, at least as far as our perspective right now. What's interesting, though, is that the maximum matching problem can be solved in polynomial time. So there is no polynomial time algorithm known to compute a minimum vertex cover for arbitrary graphs. There are polynomial time algorithms to compute maximum matchings. And so there is an algorithm by Edmonds, in fact, the same Edmonds as Edmonds-Karp, called the Blossom algorithm, that's able to compute a maximum matching of an arbitrary undirected graph in this amount, this polynomial amount of time. Now, I will actually confess that I do not fully know or understand the Blossom algorithm. The Blossom algorithm, as far as I can recall, so in a graduate level algorithms course that I took once, I was told, hey, we could cover the Blossom algorithm in this course, we just don't have 3 weeks to spend on it because of just how complicated it is. It is polynomial time, but apparently, based on hearsay pretty much, it is very convoluted and has lots of cases to consider. It takes a very long time to cover. And maximalist that I am, I don't know that we have time to cover the Blossom algorithm today. So while it's sort of interesting, I don't know that I have any burning desire to talk about it right now. Speaking of burning, though, now that we've talked about that whole refreshment deal, I guess we've been procrastinating enough. We really do need to go and put this fire out. So it's time for us to address the multi-source, multi-sink variant of the maximum flow problem. So here's a graph that has 2 sink vertices, and this is clearly a problem that's relevant to putting out that fire. I want to find a way of computing a maximum flow for this graph, but observing, as I did at the beginning, that I suppose we have to begin by asking the question, can such a thing exist? And I'll spoil it and say, yes, it turns out it can. Despite the fact that there are multiple sink vertices, there is in fact a well-defined maximum flow. There could be more than one of them, but the overall amount of flow reaching the sink vertices here is 12. Okay, so there is a way of doing that. Now, a related problem, a sort of symmetric problem that I would assume is similarly difficult, is what if you have a graph with multiple source vertices? Well, in that case, a maximum flow is also well-defined, at least in this case. Now, without theoretical results, if we approach the problem cold, we can't guarantee there will always be a well-defined result, but it seems like there is one in this case. And I think the overarching generalization, the one that we might as well address just to get it over with is, suppose I give you a flow network with multiple source vertices and multiple sink vertices. Is it possible that we can find a maximum flow for this? And the answer, as it turns out for this graph, is again yes. It turns out that there is a well-defined maximum flow. I can't really directly prove that the flow that I come up with is maximum just using this graph without a further construction, because to do so I would need the Max-Flow Min-Cut Theorem, and the Max-Flow Min-Cut Theorem is based on ST cuts with a single source and single sink. But if I sort of squint my eyes and I create this thing which I can claim resembles a sort of cut, I can observe that all of the edges leaving the cut are saturated and that the total capacity of this cut is equal to 12. Okay, so I guess that's evidence, because I can assume at least that weak duality still holds. That's evidence that what I ended up with does in fact have to be a maximum flow. Remember though that just because I can show you a particular example where there's a cut whose capacity equals the value of a flow, that doesn't necessarily mean that's always going to be the case. So this example by itself does not mean that the Max-Flow Min-Cut Theorem generalizes. And if I want to create an algorithm that gives me a maximum flow for arbitrary multi-source, multi-sink graphs, I guess if I want to approach the problem with no further adaptation, I'm going to have to prove a generalized version of the Max-Flow Min-Cut theorem. And that's a little bit scary. I don't know that I want to do that. So I guess one option, as far as computing a maximum flow, might be to modify the Ford-Fulkerson algorithm, or one of its variants, so like the Edmonds-Karp algorithm, for example, such that to go looking for augmenting paths, well, because there are multiple source vertices, and multiple sink vertices, what we could do is go looking for any path, any augmenting path between some source vertex and some sink vertex. And so I guess what I mean is sort of modify the pseudocode to look like this. So the basic Ford-Fulkerson algorithm from a couple of lectures ago said something like, while the residual network contains any path from S to T. And here I've modified it to say, okay, while the residual network contains any path from some source vertex to some sink vertex. And now the algorithm takes the collection of source vertices and the collection of sink vertices as arguments. Okay, so I can modify the algorithm to take a set of source vertices and sink vertices and perform augmentations along paths between some source vertex and some sink vertex. The question is, this is actually a pretty major modification. Would this actually work? Would the thing I end up with be maximum? What does maximum even mean? Could I write a proof of that? Wouldn't I just have to duplicate all of the proofs I've already written? And do I really have the time to do that? This algorithm is so different that I don't know that I can simply generalize. I can't just wave my hands and say that all the theorems from the last two lectures apply. So it seems like I would need at least a more general version of the Max-Flow Min-Cut theorem. Additionally, there's a bit of a running time headache lurking in the details here. So, okay, the graph has multiple source vertices and multiple sink vertices. And I, at each step, look for a path from some source vertex to some sink vertex. How do I do that? Do I loop over all the possible? So, I mean, if I have a bunch of different source vertices, so S1 up to SK, and I have a bunch of different sink vertices, T1 up to, I don't know, TL, do I just loop over every combination of S and T and look for an augmenting path? It feels like that's going to be wasteful, and it certainly looks like if I do it that way, the number of possible combinations is this number, and if the number of source vertices and sink vertices is some fraction of n, that actually is big omega of n squared. So that means that the most basic way I can think of to find these augmenting paths is going to add this quadratic factor to the running time of the algorithm. That's sort of nasty. Now, maybe there's some clever trick I could do to find paths more efficiently. But even then, I have to write a bunch of extra proofs. It does feel like this technique is a bit complicated. The technique of taking the Ford-Fulkerson algorithm and modifying it to bring it into line with this modified form of network does seem like it has a bunch of possible obstacles that might be difficult to surmount. So how about this alternative? Instead of modifying the algorithm for this type of network, can I modify the network so that all of my normal algorithms and the theoretical results I've already proven can be applied directly? And the answer actually turns out to be yes. So what I want to do is turn this network into a single source, single sink network. And once you've seen the construction, it's sort of obvious. So what I do is I add a new synthetic source vertex S, a single source S, and a single sink T. And I tie the new synthetic source vertex S to each of my real source vertices, S1 and S2, using an edge with capacity infinity. And I do the same thing with my real sink vertices. I tie them to my new synthetic sink vertex using edges with capacity infinity. Now, the idea of using edges with capacity infinity is sort of unusual, but notice that assuming I'm allowed to get away with doing this, it does allow my two source vertices and my two sink vertices to function just like source vertices and sink vertices are supposed to. So remember that one of the characteristics of a source vertex is that as far as we're concerned, it has access to an infinite supply of flow. Well, of course, this real, like the general source vertex S definitely has that property. But any flow that I'm able to get out of S1, I can pull in from S, because there's no limit to the amount of flow I can bring from S to S1 or from S to S2. Similarly, one of the properties of a sink vertex is that it can absorb any amount of flow. But that's possible here too, because any flow that reaches T1 can be passed on to T, because the edge from T1 to T has an infinite capacity. It can absorb as much flow as you can throw at it. And so under this construction, we have to treat S1 and S2 and T1 and T2 like they're intermediate vertices, because that way we can run the normal Edmonds-Karp algorithm to just route flow from S to T. But we know that the conservation rules don't really work the same way for these vertices, because S1 and S2 can take an infinite amount of flow through them, and T1 and T2 can take an infinite amount of flow and send it onwards to T. So since all flow leaving the source vertex S passes through one of our actual source vertices S1 or S2, and similarly all the flow entering this real sink vertex T, or the synthetic sink vertex T, has come from T1 or T2, a maximum ST flow in this network, if I just sort of pretend that I don't see S and T anymore, the flow that I get if I compute a maximum flow for this network does correspond to a maximum flow for the multi-source multi-sink network. Now, if you're not convinced you can prove it, and I mean you can prove it because I'm making an exercise, so one way to prove this is to show that if you have a feasible flow in the multi-source multi-sink network, so if you ignore these vertices here, if you have any feasible flow in this network, it must correspond to a feasible flow in the new network with the artificial source and sink vertices, and vice versa. So any feasible flow in the overall constructed network corresponds to a feasible flow in the multi-source multi-sink network. If you can establish that that goes both ways, then it's true that a maximum flow in one is equal to a maximum flow in another. All right, so I'm just going to say that's true and leave it there, and you'll find that the proof isn't very difficult to write. Really, it's just wrangling with notation. Now, a thought question also to consider is I've brought in the idea of an infinite capacity edge as if it's something I'm just allowed to do, and I stand by that. But as a thought question, so the way I'm using infinite capacity edges I think is completely reasonable, and as usual, if we don't like the idea of edges having literal infinite capacity, we can observe that there is a finite limit to how much flow can pass through this graph, and we could view these edges as having a capacity that's simply just a large number that's larger than any finite number that could ever be relevant to this context. What I'm wondering is there a way that I could get myself into trouble if I begin adding infinite capacity edges everywhere in a flow network? Could we create a flow network where having infinite capacity edges could get us into trouble? And to me, this feels a little bit like negative cost edges in our minimum cost path problem from a few lectures ago. How in general, negative costs aren't a big deal, but there are some cases where they can get us into trouble. Something to ponder. But in the meantime, we have what we need to put out the fire. So I now have the ability to work with multi-sink flow networks. So what I'm going to do is apply the construction that we just saw to turn this multi-sink network into a network with one sink vertex. Now to do that, I'm going to have to make up a synthetic sink vertex T. And as you can see, I'm sort of off the edge of the page here. So I'm going to ask for your indulgence. What I'm going to do is I'm just going to move over vertex T2. I'm going to pick it up with, I'm going to get some oven mitts and just move T2 over here. I haven't changed anything else about the network. I've just moved over T2 to make room for my new synthetic sink vertex T. So I make a new sink vertex T, and I connect T1 and T2 and T3 to my new vertex T by edges with infinite capacity. And now I can find a maximum flow of this constructed network in polynomial time using the Edmonds-Karp algorithm and finally put this fire out. Okay, there's our first augmenting path with 5 units of flow. There's our second augmenting path with 1 unit of flow. There's our third one with 7 units. There's our fourth one with 5 more units. And finally, we've got one with 4 more units here. We have now routed a total of 22 units of flow all the way from our source vertex S to our synthetic sink vertex T. We can easily figure out how much flow arrived at each of our real sink vertices because we can just look at the amount of flow being pushed from those vertices to T. So T1 ended up with 5 units of flow, T2 ended up with 6 units of flow, and T3 ended up with 11 units of flow. But in any event, we've managed to put the fire out. So no further augmenting paths are available, and we know from what we've seen over the past few lectures that that means that we have a maximum flow. We have routed as much water as possible to all of the vertices that were on fire, and we've put the fire out. Okay, so that means the fire is now out and the network has returned to its original state. So of course, originally, a couple of lectures ago, we had this vertex T and it caught fire. And then the fire ended up engulfing what was previously called V3 and V8. But fortunately, we've managed to remediate that condition, and so we're back to where we started before the fire. And I realized that given the amount of work that we had to do to put that fire out, I suppose it would be worth considering preventative measures. So to prevent any future fires happening at vertex T, I mean, it is orange. I'm wondering if it's still smoldering. Maybe we should make sure that vertex T is always soaking wet. Let's route the maximum possible amount of water to vertex T in advance so that there's no way that fire can spring back up again. So we're going to run the Edmonds-Karp algorithm on the original network before the fire spread. Okay, so there's one augmenting path giving us 1 unit of flow. There's 5 more units of flow, 5 more units of flow, and 5 more units of flow, and we're done. Okay, so no further augmenting paths are available, and so we now know that the flow that we have here with value 16 is a maximum flow. We can verify that by taking a look at the cut produced by looking at all the vertices, labeling as the set S, the vertices that are accessible from our source vertex in the residual network. If we add up their capacities to get the capacity of the cut, 5 plus 5 is 10, plus 1 is 11, plus 5 is 16. Sure enough, we are looking at, this is a minimum cut, and that means that this value 16 is the value of a maximum flow. Now, a sort of anomaly, though, that we should consider is, wait a minute ago, when all 3 vertices were on fire, I was able to push 22 units of flow out of vertex S across the network. So something to ponder, that's not an error, but something to ponder is, why is it that in my original graph, before the fire spread, I was only able to get 16 units of flow to my sink vertex, whereas in the multi-sink case, where all of the edge capacities, except of course for the synthetic ones to my synthetic sink vertex, all of the edge capacities were the same, even after the fire had spread, why is it that the maximum flow of my other case had value 22? So the answer is pretty straightforward, but I'll leave you to think about that. I also have sort of an uncomfortable revelation. So I didn't want to mention this when we had a fire to put out, because of course it was an emergency. But it actually turns out that shipping flow along this pipeline network, yeah, that's not free. It turns out we actually have to pay to send flow across links of this pipeline network. So it turns out that each pipeline link in my network has an associated per unit cost. I didn't bring this up earlier because with vertices on fire, that was an emergency. And during an emergency situation, we could ignore those costs. We want to spare no expense to put the fire out. But as far as preventative measures go, if I want to route water to vertex T just for prevention purposes, I really do want to avoid stretching the budget too much. All right, I want to save my firefighting budget for emergencies. So now that the fire has been put out, we sort of have to consider this situation. So just to clarify what I mean about per unit cost, you'll notice that now each edge has an associated dollar amount associated with it. That is going to be the amount that it costs to route 1 unit of flow along the edge. So if we look at the edge V2, V3, it costs $8 to route 1 unit of flow. In the particular flow assignment I'm looking at, there are 5 units of flow across that edge. So the total price of this flow across edge V2, V3 is $40. The number of units of flow multiplied by the per unit cost of $8. If I want to work out the cost of the entire flow assignment overall, over the entire graph, all I have to do is to go through all of the edges and multiply the number of units of flow by the cost of routing flow along that edge. And it turns out the total cost of the flow I just created, the maximum flow with value 16, is $338. Okay, fair enough. But I can't help but ask the question, I certainly don't want to sacrifice the maximum flow. I want to route 16 units one way or the other. But is this really the least expensive maximum flow? In other words, could I come up with another flow, F prime, that still routes 16 units of flow, but where the total cost of that flow is less than $338? This is something that we ought to be able to do. We know about dealing with minimum cost stuff. This seems like the kind of problem we should be able to solve. And we will solve it. But that's a topic for the next lecture.